We're Team EasyVent, and today we're excited to share with you an AI method for helping physicians optimize ventilator settings in the ICU. Mechanical ventilation is the cornerstone of critical care medicine. However, despite decades of research, choosing the optimal ventilator strategy for a patient remains an imprecise art. Existing guidelines provide one-size-fits-all recommendations but do not personalize treatment for different ICU patients. There is still much uncertainty when choosing optimal levels of positive and expiratory pressure, fraction of inspired oxygen, and tidal volume for a particular patient. Stakes cannot be higher, as wrong ventilator strategy may end up harming patients who are already fighting for their lives. But what if we had an AI system that could understand the complex interplay of variables in different patients and help physicians choose an optimal treatment strategy both at the start and during the course of mechanical ventilation? Reinforcement learning, or RL, is an AI method that can do that. In RL, a computer agent collects experience from a huge database, far surpassing the experience of any human. This ability of RL to learn complex sequential decisions makes it suitable for the critical care setting, and we hope to use its capability of learning to provide individualized and clinically interpretable treatment policies that could improve survival for mechanically ventilated patients. To do this, we analyzed both MIMIC-4 and eICU databases. For critically ill patients aged 16 years and above, receiving invasive ventilation for at least 48 hours. Only the first ICU admission or the first hospitalization for each patient was included. We excluded any patient who had tracheostomy operation or was extubated or died during the first 48 hours. This is a patient flow chart from the two databases. After excluding patients who are missing demographic and ventilation data, we ended up with around 11,000 patients in the eICU cohort and 3,000 patients in the MIMIC-4 cohort. Next, I will talk about our RL design. We constructed our state space with these variables to reflect the health status of a patient in every 4-hourly window. The action space was constructed as 18 possible discrete actions from the combinations of low, mid, high categories of the 3 ventilator settings, PEEP, FiO2, and tidal volume. Part of our RL model reflected the objective of the RL agent, which is to maximize survival and to keep certain blood gas and vital signs within optimal ranges. Hospital mortality was used as a terminal reward, whereas oxygen saturation and mean blood pressure were applied as intermittent reward. We trained various RL models on the MIMIC-4 dataset and tested them using the eICU dataset. Here in the bar chart, the blue bars represent the counts of physicians' actions, and the red bars are the actions recommended by the RL agent. We found that the actions chosen by the RL agent did not always agree with those made by physicians. To evaluate whether the RL agent or the physicians made better choices, we visualize our training results as follows. Here, the top red graph shows mortality rate versus the discrepancy between RL action and physician action. Ideally, if the physician chose the same action as the RL model, the discrepancy will be 0 in the center of the curve, where we found the mortality rate to be the lowest. This would give a V-shaped curve, which we found for all 3 ventilator settings using our RL model. The bottom green plot shows the relationship between mortality rate versus the concordance rate. Say, if a physician always follows the RL recommended action, the concordant rate will be 100%, where mortality is lowest. To examine the robustness of our findings, we trained our RL agent using MIMIC-4 and tested it on the eICU cohort. In addition, we compared multiple RL models, including BCQ, FQI, and dueling DQN. We found that the estimated mortality rate was consistently lower when the RL policy was used compared to both physician's policy and the actual mortality in the validation dataset. On average, we could potentially reduce mortality rate by 2.7% if we followed the RL policy. Considering that there are millions of ventilated patients per year, this could mean thousands of lives saved every year. Acknowledge that there are still many areas of improvement, and moving forward, we hope to change our fixed time windows to flexible time windows according to action timestamps. We hope to do state action bubble analysis and missing data sensitivity analysis, and also to perform further comparisons for more RL algorithms. Ultimately, we aim to design and validate a real-world clinician decision support tool. Thank you for your time and support.